If I focus really hard, do my powers of quantum mechanics allow me to manifest reality? No. But then why did some of the founders of the theory seem to think that consciousness and quantum mechanics were inextricably linked? The behaviour of the quantum world is beyond weird. Objects being in multiple places at once, communicating faster than light, or simultaneously experiencing multiple entire timelines that then talk to each other. The rules governing the tiny quantum world of atoms and photons seem alien, and yet we have a set of rules that give us incredible power in predicting the behaviour of quantum systems, rules encapsulated in the mathematics of quantum mechanics. Despite its stunning success, we are now nearly a century past the foundation of quantum mechanics, and physicists are still debating how to interpret its equations and the weirdness they represent. It's not surprising that the profound weirdness of the quantum world has inspired some outlandish explanations, nor that these explanations have strayed into the realm of what we might call mysticism. One particularly pervasive notion is the idea that consciousness can directly influence quantum systems, and so influence reality. Today, we're going to see where this idea comes from and whether quantum theory really supports it. To start, we're going to need to go back to one of the earliest interpretations of quantum mechanics, the Copenhagen interpretation, often associated with Niels Bohr and Werner Heisenberg. It tells us that the very act of measurement or observation causes an experiment to settle on a particular result, and that it's meaningless to talk about a well-defined objective reality before that measurement is made. Let's see where this kooky idea comes from, using the classic example of the double-slit experiment. It goes like this. A single electron is shot at a pair of slits. It passes through and is registered on a detector screen on the other side. When multiple electrons are shot, one after the other, they form a series of bands. That's the same pattern that will be produced by a wave passing through both slits, a so-called interference pattern. But that's weird, because this interference pattern seems to guide the path of every electron independently of the others. Each solitary electron must know the entire wave pattern, which means it must, in some sense, travel through both slits. The Copenhagen interpretation explains the result of this experiment by saying that the electron does not travel as a particle or as a physical wave along one of these paths. Instead, it travels as an abstract probability wave, something we call a wave function. That probability wave defines the location of the electron at any point if you try to measure it. The Copenhagen interpretation states that prior to measurement, it's meaningless to talk about a real physical state for the electron. It exists only as the possible outcome of a future measurement. Prior to measurement, it is the wave function. Copenhagen tells us that when we make that measurement, the wave function collapses. It goes from a cloud of possible final destinations for the electron to a more or less definite spot on the detector screen. Wave function collapse seems essential because our large-scale classical world isn't made of probability clouds, it's made of objects with clearly definable properties. So when does the quantum transition to the classical actually happen? Let's look at the process in the case of the double-slit experiment. The electron wave function passes through both slits, reaches the electronic detector, and there it excites a second electron somewhere on the detector screen. That second electron begins a cascade, an electrical impulse that travels along circuits to be registered by a computer, which updates an image on a computer screen to show where the electron hit. And that information travels via photons to light-sensitive molecules in our retinas, which initiate electrical signals to our visual cortex, and more electrical signals in other parts of the brain result in a subjective sense of the original electron's chosen destination on the screen. We call this chain of information between the detector and the mind a von Neumann chain, after the great Hungarian-American physicist John von Neumann. He wrote that wave function collapse must happen somewhere between the measuring apparatus and the conscious awareness of the result of that measurement. But exactly where? Probably not as soon as our electron wave function reaches the detector. The first electron to become excited in the detector is also a quantum object. That means the travelling electron's wave function will just become mixed with the wave functions of all electrons that it could possibly excite. We should get what we call a superposition of states, a wave function in which an electron at every location on the detector screen is simultaneously excited and not excited. So perhaps the wave function transition happens somewhere in the circuitry, or in the computer, or in the retina. But all of these things are made out of atoms. The von Neumann chain from detector to mind is a chain of quantum objects. With no clear boundary between the quantum and the classical, where does the collapse of the wave function happen? We call this open question the measurement problem. John von Neumann believed that the wave function collapse must happen at the moment of conscious awareness of the result of an experiment. Another of the greats of early quantum theory agreed with him. Eugene Wigner was a fellow Hungarian-American and actually went to school with von Neumann before they both ended up at Princeton. The idea that consciousness collapses the wave function is now called the von Neumann-Wigner interpretation, and it's sort of a subset of the Copenhagen interpretation. In 1961, Wigner devised a thought experiment to argue for the role of consciousness. The Wigner's friend experiment goes something like this. Suppose you don't conduct the double slit experiment, your friend does. You know the experiment has been completed with a single electron reaching the detector, and your friend is aware of the result, but you are not. So, we have an extra step in our von Neumann chain. Before the information about this quantum experiment reaches your conscious awareness, it has to pass through your friend's conscious awareness. So we have this weird moment, somewhere between the landing of that electron on the screen and your friend telling you the result. From your perspective, your friend's entire brain exists in a quantum superposition of all possible results of the experiment. Only after your friend tells you the result of the experiment does their brain wave function collapse to a single experimental outcome. So, you ask your friend, what was it like for your whole brain to be in a superposition of states? Well, they think you're crazy. They tell you that the wave function collapsed as soon as the physical experiment was completed. But there was no way for that collapse to have happened from your perspective. No information had reached you. So there's the conflict. Different observers say the wave function collapses at different times. Eugene Wigner felt that this conflict meant that it was impossible for entire brains, or more importantly, conscious experiences generated by those brains, to be in a superposition of states. Therefore, he concluded that conscious experience must itself play a role in generating wave function collapse. Wigner and von Neumann weren't the only ones who questioned the relationship between the mind and the measurement problem. Wolfgang Pauli was perhaps the first to assert the connection, and his influence may have started the development of the Copenhagen interpretation, later attributed mostly to Bohr and Heisenberg. Bohr himself was careful about claiming any direct role of the conscious mind, and vigorously defended himself after Einstein accused him of introducing mysticism into physics. But Heisenberg was more open to mystical interpretations and the direct influence of consciousness, at least early on. Even Erwin Schrödinger, in his 1958 lectures Mind and Matter, states that consciousness is needed to make physical reality meaningful. With the greats of quantum physics inclined to speak in these mystical terms, it's not surprising that the ideas stuck around. In the 1970s, books like The Tao of Physics and The Dancing Wu Li Masters drew parallels between Eastern mystical traditions and quantum physics. On its surface, that seems like a nice idea, poetic descriptions of the mysteries of physics with philosophical musings. But these works really opened the floodgates. Self-help books and documentaries proliferated, making all sorts of claims, like that you can influence reality by acts of will, collapse the wave function in your favor to force the location of a spot on a screen, or influence the shapes of snowflakes, or get a promotion. And then there's the idea that external reality doesn't have an objective existence. Our minds invent the universe. But, as Richard Feynman said, if you think you understand quantum mechanics, you don't understand quantum mechanics. The more you know about this theory, the less likely you are to pretend that you fully understand its deepest implications. And yet, the most confident claims about quantum mechanics seem to be the mystical ones. They tend to be made by people who have never studied the theory deeply, but nonetheless have great surety in cherry-picking and misinterpreting the early speculations of some of its founders. Those founders did question the role of consciousness and the connection between subjective and objective reality, and they were right to do so. The weird behaviour of the quantum world demanded the courageous and open-minded speculation that characterises a great scientist. But the other quality of a great scientist is openness to changing your mind. And most of them did change their minds, veering away from the idea of a direct causal role of consciousness. In Heisenberg's later writing, he states that the wave function collapse must be a continuous process between the measurement device and the conscious mind, and definitely not a sudden event caused by the latter. Wigner too, he switched camps and spoke against the notion of the primary role of consciousness. He denied what he called the solipsistic view that the mind is foremost, that consciousness generates the universe. In fact, we can use Wigner's friend to put to rest the worst misinterpretations of the Copenhagen interpretation. This time, you stand next to your friend and you perform the double-slit experiment together. A single electron reaches the detector screen and you both learn its location at the same time. You talk to each other and you agree you observe the same result. The wave function collapses in the same way for both of you. So what? Maybe one observer is forcing their preferred wave function collapse on everyone else? Or maybe you are the only observer and you're inventing your friend and, well, the rest of reality, and there are no other observers in the universe to give conflicting results. No, the only coherent explanation for the consistency of experimental results between different observers seems to be that the result of the experiment and reality exists independently of individual observers. Sure, you could talk about a global consciousness collapsing a universal wave function, but that's not going to give you any powers of quantum wishing. Despite not having settled the measurement problem, at least not with full consensus, modern quantum theory has come a very, very long way since its foundation. In fact, there are some very precise explanations for why the wave function appears to collapse. And conscious observation may play a role, but not in the way you might think. To understand that, we need to understand what happens to these multiple alternate histories after the electron wave function reaches the detector, and why these histories stop communicating with each other. We need to learn about quantum decoherence and the quantum multiverse. For now, one thing I can say with certainty is that your own future wave function includes a deeper dive into the quantum classical divide on an upcoming episode of Spacetime.